So, welcome to everybody. Bem-vindos. It is a great pleasure to have here Professor Jacob Palis from the Instituto de Matemática Pura e Aplicada in Rio de Janeiro to give the Pedro Nunes lecture. So, on behalf of the Centro Internacional de Matemática, the Sociedade Portuguesa de Matemática and the Centro de Matemática do Instituto Porto, I'd like to welcome you here. Thank you for being willing to come to give this lecture. So, of course, I guess everybody here knows very well Professor Jacob Palis, and don't need to tell you very much about him, but certainly it's a pleasure to have here this great mathematician to talk to us. Thank you.
Thank you, but eu não sei se fala em português ou em inglês. Inglês? First of all, it's a great pleasure for me to be here. I have been coming to Portugal since '82, and so I'm very passionate in the mathematical community of Portugal. I have several students or former students, and so on. At least one more generation, I don't know how many, 2 or 3 maybe. I am here with great happiness and always very supportive of the development of mathematics and science in general in Portugal. And so please consider me as one of you. Well, my work in dynamical systems goes way back to the middle 70s, where when I was in Berkeley, in California, and I decided to look in the question of stability of dynamical systems, especially orbit stability, and I was very lucky to find a way to consider this problem in a situation where it was not very homogeneous, and so it went a long way after that. And at that point, my advisor, Steve Smale, a very well-known mathematician, had the idea that began actually with Poincaré, of trying to define what would be a typical behavior for dynamical systems. The first to point out, not in a clear, very well-formulated way, but certainly a definite way, was, as I said, Poincaré. After that, there were other tries, and finally we had Smale suggesting that what we call hyperbolic systems, which will appear in a moment, would be typical. Well, that conjecture did not last much time. 2 or 3 years later, he himself and others were proving that there were systems that are not hyperbolic, and you could not approximated by a hyperbolic one. So I'm mentioning a topology in the space of dynamics. That's not very complicated. What we do is we assume the dynamics to be differentiable up to a certain order, and then the metric there would have to do with how near are the dynamics pointwise and their derivatives up to that order. It's a very simple, very efficient definition. So there are, in other words, there are open sets of dynamics such that no dynamics in there is hyperbolic. Now, all these terms will be more precisely defined in a moment, but I want to throw right away the perspective on the globality of dynamics. So first of all, for me, dynamics will be transformations of a differentiable manifold. So it's a nice piece of Euclidean space, if you wish. It will be a finite dimension, except when I say to the contrary later on. And so I'll consider maps that have inverse homeomorphisms, and they'll be differentiable. So we call them diffeomorphisms. Or else, just differential equations, simple ones, generating flows. And so we have either diffeomorphism or flows. Now, I'll assume, as I said, that they are differentiable, at least one differentiable. And then I'll look into the space of dynamics. That means I define in the set of all dynamics when two of them are closed pointwise, and the derivatives are closed up to the order of differentiability. Then back to the dream of Smale, that was really a dream of Poincaré, was to say not the behavior of all dynamics, but the typical ones. So we have to define what I mean by typical and try to look into that. It would be, it's not reasonable to try to understand all dynamics. So from that point on, there was a lot of developments in dynamics in the 60s concerned with, as I said, stability questions and concepts derived from that, like hyperbolicity and so on. Now, by the end of the 60s, I start reading a lot of the work of Poincaré, and at one point he refers dramatically to what we call bifurcation of what we call homoclinic trajectories. He was looking to, of course, celestial mechanics, and he had to face this kind of questions, and to him was something very dramatic, because he missed the point at one paper, through which he won a special prize. And he had to go back, because someone pointed to him, I don't understand your reasoning, and he was wrong. And so this, I kept that in my mind for quite a while, and I decided together with a few other colleagues to pursue a different line in dynamics. So it was like having two lives. And the second one really took me to look into change in dynamics. Now, like you say, evolution, Darwin's evolution, and, or the theory of Marx, you see evolution and bifurcations. Well, that's what we deal with, not in political terms. At least I didn't apply to political situations. But to me, all these three ways of thinking are similar. I don't say equal, so I may offend social scientists, but I didn't get good answers from a number of them when I said that there is a parallel between these three ways of thinking. Anyhow, to go that way, we had really to go into fractal dimensions. You're going to see Hausdorff dimension here, especially. And we had to adopt, which was already quite developed by the Russian school, which was the theory of probability. And so this, putting all this together, it took something like 20 years of very nice examples and results. And so finally, in 1995, I was, as always, very audacious, not knowing exactly what I'm talking about, but knowing the direction. I put the question of what would be typical in dynamics. And behind the proposal is the idea that in many, many cases, that's not really new, we have uncertainty in the models of natural phenomena and others. But the idea behind it is that if my proposal is correct and is being proven to be so in a number of situations, not yet the whole thing, we would be able to estimate uncertainty in these models. So the potential for applications is certainly not small, to talk like the British, double negative. So that's what I'm going to present to you now. Well, how do I start? I prefer here. As you can see, I am a dinosaur.
This one fell asleep.
I hope it comes.
It takes a while.
Yeah, so all these I have mentioned before, except that we shall consider what I said in parameterized terms, which is a good way of looking at this question of what is typical. And so I'll move on. Okay, then I call the attention of the vague probability playing a role all the time there. Yeah, so again, Uh, uh, I would look for the typical dynamics in the sense of, that, as I said, the phase space is compact, no boundary. This can be extended to the non-compact case, but let's focus the compact case, no boundary. And I want to look at attractors. There where I'll talk about uncertainty and how the trajectory. So I start in a certain point, I apply the dynamics many times. I want to know where it goes in the future. So it's really a question of trying to predict the future. That's why the interest of that certainty. I'll keep making mistakes all the time. So, forget about the technical expressions there. What is important is in the space of dynamics, I say that there is a dense set with only finitely many attractors. I'll define attractors in a moment. But that means, well, I can advance the explanation. It's just a set which is invariant by trajectories of these dynamics that attracts all nearby trajectories starting near it. All nearby trajectories go to this set. Then we call this set an attractor. Well, of course, I want a dense orbit in the set so to avoid that it can be split in several attractors. Now, the second term is quite sophisticated but important, but I won't go into that. We have some specialists in the house about what is called a special invariant measure named after symmetric Bowen. The stochastic stability is a classical also concept. But it's not very important. It's not the main point in this lecture, so I'll jump it to avoid technicalities. This is important. The last one point here that typically we are going to see attractors with nice properties. Okay, I like this little figure very much. So I'm talking about parameter space, finite dimension, cross the phase space where I'll look into the set of transformations of this space, which will be a differentiable manifold. I'll assume the transformations to be differentiable, and often with a differentiable inverse, the case of diffeomorphism. But in the case of the interval, I'll allow transformations also without inverse, otherwise it would be, well, much simpler. Now, if you consider a parameterized family of, say, diffeomorphisms or flows, then what I'm saying is typically in the parameter space, that means with total probability, and that means Lebesgue probability. One, I'll have the corresponding dynamics in the phase space to have only finitely many attractors. This is an attractor, so just a point attracting all orbits nearby. Well, this is the case of flows, so periodic orbit may be attracting. And this is the novelty, what is called Lorentz attractor. I'll talk about it more specifically later. You see, from the important idea of being hyperbolic as proposed by Smale, we went quite far from it with a number of examples. And one was Lorentz, that you probably heard about, butterfly. Lorentz butterfly was fundamental. And there is another one named after an astronomer called Nunes. Anyhow, we have a finite number of attractors. This is compact. And moreover, I'll say that with total probability, the trajectories in the phase space will go to one of these attractors. Not only one, will go to the attractors. I may have some divisors, but that I don't know where the orbit goes. I won't say where it goes, but it doesn't matter. That will have zero Lebesgue measure. So I don't care about that. So the idea is to say a fundamental quality of typical dynamics in the sense of having only finitely many attractors, and also module zero, volume zero, all the trajectories will go to these attractors in the future. And there, each attractor will have a certain uncertainty. That's simply the diameter of the attractor. So if we know that this is true, what I'm saying is true, then of course people in applied mathematics or else, or some smart physicists will chase immediately where the attractors are, and they will certainly be able to estimate the diameters, and that will mean an estimation of the uncertainty of the model. And that's really what I am interested in, estimating uncertainty of future behavior in many of natural problems. So it's quite ambitious, but why not? So when I put this program, 95, of course I have chosen Paris to do so, and an important meeting in dynamics in honor of Adrien Douardi. And as even before the lecture was ended, as I expected, many people in the audience tried to give counterexamples immediately. So I had stones and eggs. I have been surviving very well for 16 years. It's still not there, but it's coming. It's slowly, it's coming. So, in the case of one dimension, this is completely solved. It's highly non-trivial. We had many important works, mathematicians connected to that. And finally, the answer was complete by Arda de Mello, Lubitsch, and Arda and Morera. So this is a case of one dimension. Of course, now instead of diffeomorphisms, we consider just transformations, CK transformations, K at least 2. However, there is a limitation, which is only one critical point. So even in this case, there is quite a challenging question concerning transformations of the interval with several bumps, with several critical points. I have been losing bottles of champagne on that because I thought that would come quickly after the case of one critical point. So I lost two already. I bet another one that will come. Well, I'm enthusiastic, but I have to tell the truth. It's not a simple program. Now, quickly, well, you see what attractors are. They attract all orbits that start nearby. It's a subset invariant by the dynamics and attracting all nearby orbits. Well, you know, you can say little sophistication, attract a set of positive nature, always Lebesgue in the neighborhood. Okay. Now, this is Lawrence. I'll mention quickly. This is very famous. So Lawrence, that's an interesting story. 1963, he was looking to, together with other people. One is never alone in this. And the prediction for the weather in the future, or the climate, which is a little farther in the future. And so he came to a set of equations truncating from an infinite dimensional system. And he checked with a simple machine that was available at that time, not really a computer, two very interesting properties. One was that, so you can see that 0, 0, 0 is a fixed point, and it's not linear, the system, but it's just quadratic. Yeah. And one of the properties he notices that with total probability starting, he didn't use this word, but it's now the way we say it. Start with the nearby points of a figure that seemed to be an attractor to him, and it was. In the future, the orbits would split apart as much as the diameter of the butterfly. That was one thing. Second is that he changed a bit these coefficients and seemed to get the same similar situation. Not same, but similar situation. An attractor with this property that we call chaoticity. With total probability of points nearby, the future orbits will spread apart as much as the diameter. This is already a counterexample to Smail's conjecture, but we didn't know. It was like next door, but no communication. And so, so in 1963, it was already proven that the non-hyperbolic systems contain an open set. These are not hyperbolic, for sure. I'm not showing it, but I'm saying it's not hyperbolic. No chance of being hyperbolic. Hyperbolic means, let me jump, the much complete, simple situation. Okay, now there is some, doesn't matter. Hyperbolic means that along trajectories, you have some contraction and some expansion, in complementary dimensions. That's all. If this is systematic, then you say the system is hyperbolic. In the case of flow, there is one more dimension along flow. Well, then along the direction of the flow, you don't say anything. It's like neutral. Then in the complementary to that, the complementary dimension, then it splits up into subspace where you see contraction, and another subspace complementary to that where you see expansion. So that's what is hyperbolic. So let's go back there. So Lorentz is not hyperbolic, and at the same time is open. Well, sometimes we call robust. So then the hyperbolic systems are not dense, are not typical. Then 1975 or so, an astronomer called Nunes, he tried to imitate Lorentz, but now for diffeomorphisms of the plane. So again, he considered just contraction, degree 2 in the plane, that would take a disk of big radius into itself. And so if you keep on, you get a tractor. Now, for certain values of A and B here, again, experimentally, he conjectured that you have an attractor which is not just a simple periodic orbit of large period. So you cannot just draw a picture and decide if it's a line that expands and folds, or a point with a very large period that almost fills, and it may take you to be wrong, to have the wrong idea. So this was later proved to be true, that there is such attractors. You have some fractal dimension transversally, and this is not open. So if I change for a certain values of A, B, and B, if I change a little bit, not necessarily I get the same kind of attractor. I'll get a periodic one, very large period. But this probabilistically persistent. So for some set of positive measures in A and B, you do get an attractor like that, which is not periodic. So again, it's not hyperbolic. It's not very hard to see. And so this is another important example of non-hyperbolicity. Again, hyperbolicity means contraction and expansion all the time. You don't have it here. Now, it's interesting to say that it took 10 years or so from the 75 to 85, 86, to prove that this was so. That this is really a concrete example, not just a proposal. And involved on that, there is Carlson, Benedict, to Sweden, but also Marcelo Viana played an important role in that. And someone from Venezuela. Okay, so let's go on. Now, back to Poincaré, there is the idea of cycles in dynamics. this line was not there. But this morning I went to a museum here, and there was an exhibition by an artist that separates the picture. A separatist, so it seemed that I was starting to do it, but I didn't do it. Anyhow, so you can imagine this to be a diffeomorphism on the surface, depending on the parameter, and then this line, which is made of points that in the future go away from the fixed point, start touching this line of points that in the future comes to here. So when they go away, we call unstable. When they go in, we call stable. So you see, the way to do so is to have a tangents to begin with, and then to cross like here. Now, this disappeared for some problem about the program used, but imagine that this point is equal to that one. Or maybe I have a data. Here? Well, that is really against it. You see, in Brazil, it's very common to use Microsoft, and I see that the Europeans hate Bill Gates, so always some problems. Okay, also survive. So you imagine these figures, imagine that S1 equal S2, then we call this point homoclinic. That means this. So here is like if S2 equal S3. So this line of points going away. So we have expansion here. March in the future, that's the line of points going in. If you consider the derivative of the map, at this point you're going to see an eigenvalue bigger than 1 and one smaller than 1 in norm. So, so it's very important in dynamics to consider cycles. The trouble with Poincaré, I mean, of course, he is our greatest predecessor, but he made a mistake concerning homoclinic orbits. He took very few derivatives and concluded in some case that the two lines would be equal, which is very rare. It's clearly very rare. And that was his mistake. So in Nouvelle Méthode de la Mécanique Céleste, there is one page that what caught my attention, a very dramatic page where he says, you know, the hard part of dynamics is in this phenomenon. I never forgot that sentence. So I still dream with it every evening. Because it's really the key to dynamics is to understand this process where you are moving a parameter and then you go through a homoclinic tangent and then you make it transversal, this line. When you do that, you see a dramatic change in dynamics. When I was playing a little bit in a very loose way with Darwin and Marx, what I meant here is that the change in dynamics is very dramatic. And it is still a challenge for us to fully understand this. So that's an important point here. Now, you can think of this in higher dimension. I don't know if you see clearly here, but in this case, what I try to show here is one dimension of points coming in and two dimensions going out, that way and that way, and vice versa here. And somehow I create a cycle where here is the dual one, two dimensions coming, on only one dimension going out, and they cross. So it's really dual situations crossing here. Now I don't have to make tangents. Here, since this is one dimension and this is one dimension, there is a missing dimension. The total dimension is 3, so we don't have transversality. Okay, so these are the two crucial elements, no more than that, to set up the program for dynamics. So, now how do you go about proving what I suggested at the beginning? Would be not, well, to me, not very satisfactory. Just set up a conjecture and not to give other parallel conjectures to indicate the way, the avenue to prove it. So this all came together. So the idea is that what we have to, is there something missing here? I hope not. Oh yeah, okay. Yes, we would be able to prove the conjecture that is finitely many attractors and almost all orbits going to the attractors if we do not see any homoclinic tangents or heteroclinic cycle. So I'm avoiding the existence of homoclinic tangents or heteroclinic cycles. I am saying if I have some spot in the set of dynamics where these two elements are absent, then I should be able to prove the conjecture. That's the way to prove the conjecture. And that is, I would get from this absence of homoclinic tangencies and heteroclinic cycles, I would have some form of hyperbolicity. And that's in the case of hyperbolic systems. We know that what I said is correct, and that is not new. And then what I will have to pursue, the proof of the conjecture will be near the unfolding of these homoclinic tangents or heterodimensional cycles. That's exactly what I was pointing to. If I have some hyperbolicity, strict hyperbolicity, I know everything. I know since the 60s. I don't have to prove anything. What I said is true. Finitely many attractors, and most orbits going to that attractor. So, I look at what else do I have to explore? Well, I say if I see some homoclinic tangencies, then two things. If I unfold it, then I show that, so I make it transversal, I show that it's true for many situations near this unfolding. Okay, or else I have an absence of this, and that is I have some kind of hyperbolicity. So it's one of the two. Or I introduce also these dimensional cycles. So in other words, the conjecture leading to this way to solve the problem is that any dynamical systems can be approximated by a hyperbolic one, then I know that's true, the conjecture, the program, or one with homoclinic tangents or a paradimensional cycle. Now, if I get the second part, then that's what I'm telling you. If I unfold it, I destroy it a little bit, then I'll show that in the neighborhood of it, this is true. Then I'll be complete. Now, conjecture 1, at least for R equal 1, has been proved very recently by Pujals and Provisier, two names that are here. The second conjecture is not, I won't talk about it, it's an interesting one, but it's not relevant to the proof of the main conjecture. But the conjecture 1, yes. The second very important and beautiful result is that also very recent, is not published yet, and is due to the same people, Provisier and Pujals, says that any diffeomorphism can be approximated by one that is essentially hyperbolic. It's not very important for you to know what is essentially hyperbolic. What is important here is the word hyperbolic, some form of hyperbolicity. Okay? Now, this is true. The limitation here is in the C1 topologies, that has to be improved. But once you have that, then look at this. You have a finite number of attractors, and the union of the bases of attraction, it's open and dense. I didn't say open and dense, I said total measure. They already know how to prove total measure up to dimension and including 3. So that would be it. A little more effort here. Another bottle of champagne, we will have the complete program, at least in the C1 topology. Now, for R bigger than 1, there are efforts coming from dimension 1, the case of one bump, one critical point, as I mentioned to you, and going to dimension 2, and that is it's a long-range program, but it's successful, and that a number of people are involved. So there are two fronts. In the case of the C1 topology, we are almost there due to these results. And in dimension 2, the progress is very good, but is step by step. Going to dimension 2 then to go up into higher dimension. It will take quite a while. According to Lubitsch, 6 months ago, a little more, 10 months ago, they organized a meeting in connection with my birthday, and he said, when I was 70, he said, when you are 80, we'll be half the way, and then 90 will 4/5, and then 100, we have everything. Thank you very much. I guess I should give you some reference. Oops. Oh, back to 0. Wow. And now what?
There's a computer expert in here.
Well, I'll leave this here,
Yeah.
also in written form,
Yeah.
and the reference on that.
So maybe it can be. If you want to
I
share
think I
the-
did it too quickly.
To go to. Stop me.
Little more.
Little more.
Almost helps.
Yeah.
Right.
Okay.
Thanks a lot.
Great. So I don't know if maybe there's time for 1 or 2 questions. If
Yes, please.
somebody wants to comment or question.
Oh, it's incomplete.
Yeah.
That's a page or 2.
I have one question.
Please.
I do not know nothing about the one-dimensional case about Lubitsch, but there is a way of bypass the pure closing lemma or Hayashi closing lemma to get the C2 or at least
Yes.
C2?
Well, the closing lemma, well, there is something in dynamics which we call closing lemma. That is when you have an orbit that goes in the future very near the initial point. The question is, can you perturb your system in CR way for any R, say C2 close, C3, C4, etc., to make it periodic. So to close it, that's why the name close it. Yes, this is the main obstacle. We know this in general only in the C1 topology when we try to control C2, second and third, and so on derivative. The situation is unclear. However, certainly they went around very well in the one-dimensional case. That's for sure. So the question is not that in one dimension, including for many bumps, you have the density of the hyperbolic ones. That's why in the CR topology, NR. That's why I keep losing bottles of champagne, because to me it should be there, the final proof, but there is still some obstacle. Now in higher dimension, for a long time, I defend the thesis that we don't have to prove this result in general, but to focus in the questions we have. You see, to deal with this kind of question, making an almost periodic orbit to be periodic by moving a bit the system. On top of, you see, there is a lot of structure here. So my point is to defend this. It will be harder, but you should not try. It doesn't depend on the abstract, the proof of the closing lemma in abstract, just by saying, in any case, if the orbit goes back near the initial point, then you can make it periodic. We have much more structure here. So it would be nice to have the closing lemma, but I don't think I share with Lubitsch or Lubitsch share with me. I was older to say these things. But anyhow, we share the idea that you have to work with the structure you are setting directly. That's what him and others, Martins, and so on and so forth, are trying to do.
I'm going to ask perhaps an absurd question, but anyway, let me try. You mentioned at some point uncertainty related with behavior of the system.
Yeah.
And I'm a physicist. Uncertainty to me is very much connected with quantum mechanics. So is there any way one could envisage to get the uncertainty of quantum mechanics somehow, or a simple quantum mechanical system with this classical system?
Yeah,
They're
well,
completely different.
when you mentioned that you are a physicist, I sort of knew you were going to that. I don't know, but certainly we should be able to match these two things. It's since the physicists are very smart.
Well,
No, I
not
believe
all
it.
of them, not
No,
all
no,
of
I'm
them.
serious.
That is not my case.
Yeah, no, usually very smart. No, I think we should bring, well, you know, of course there should be a connection there. I didn't think about it, but we should talk more. Certainly, the basic idea should be the same. But I forgot, since you motivated me to go into a point which I promised and I didn't say anything about it. One case that I really am passionate for is the turbulence. If I'm saying, well, uncertainty, so one of the certainly wonderful example is turbulence, besides, of course, climate and weather prediction. On turbulence, I have been asking people, actually I attended a few nice workshops on turbulence. And the main people around, at least the ones I met, say that my ideas seem to fit the experiment. So this is very encouraging. From the theoretical point of view, if all the main conjectures are true, then mine is also true in this context, which are the following. So if you look at evolution equations, this is infinite dimensional dynamical systems, we go on to the future. Then one of the conjectures is that for most initial points, you have complete orbits. So orbits don't collapse at a finite time, so you can go on. The second conjecture, both are proven in special case when you have a lot of dissipation. The second case is, the second question is complete solutions, so solutions that can be defined for all time. They will converge to a certain, in each case, to a certain finite dimensional space. That's another main conjecture in the field. Also proved to be true in the hypothesis of dissipation. Now, if you put the two together, then if they are complete, solutions for most initial points, the solutions are complete, and they go to a finite dimensional space, then you are in business here. You're bound to see finitely many attractors in a finite dimensional space. And with most of these complete orbits going to this attractor. So anyhow, no one says so far that I'm crazy. They seem to find reasonable what match the experiment. There's another interesting situation which I was told by David Mumford. David Manford is a very interesting mathematician. He started in number theory and algebraic geometry. Got a Fields Medal, I forgot when, 72. But more recently, he moved into vision, computer graphics, but more vision. He tells me that when you collect many data, so one problem people like to deal with these days is to collect a lot of data, and then they plot it and they want to say something. Well, he tells me that there seems to be in these many situations a concentration of this data in certain spots, which again would fit the idea of finitely many attractors. I don't know, we'll see.
More questions? Okay, so thank you very much again for
Thank you.